Okay, so what we're going to talk about this morning is the idea of how you can improve the performance of Cassandra. And so what we need to look at is, what do we mean by performance? What are we actually looking at here? So the first thing is, let's just briefly recap on Cassandra. Now, assume that people who are watching this presentation are already using Cassandra, so we don't need to spend time really discussing what Cassandra is and the details of that. Cassandra is a NoSQL database, and the important thing about that is it scales elastically, and that's really the key point, is the scalability of Cassandra and being able to guarantee that in terms of how it runs. The other thing that Cassandra provides to us is the idea of sub-second response times, the idea of very, very quick response times, again, with scalability, which is linear. So you can add more nodes, you can add more load to the system and get linear scalability. One of the key things about Cassandra is that it runs on top of a Java virtual machine. So it's written in Java, it uses the Java virtual machine to execute. What that means is that even though the code for Cassandra can be, is excellent code, it's been very well written, very well tuned, the actual Cassandra that runs is subject to the traditional JVM performance issues. And these are things which have been around right from the beginning of Java. One of the things that we see a lot with clients who use Cassandra is that they try to adapt what they're doing in terms of their deployment to cope with the way that the Java virtual machine works. So we often see customers using smaller heaps than they really want to in order to reduce pauses. Some of the other things that we see related to that are that people can sometimes experience administration problems due to pauses which are introduced by the JVM. Things around cleanup, things around repair tasks, even being able to orderly shut down a cluster of Cassandra nodes can be affected by the way that the JVM works. So what we're going to do in this presentation is talk about how we can solve those problems. So the first thing we need to do is look into JVM performance a little bit. We need to talk about what are the issues that you as a Cassandra user face in terms of using the JVM, and then we'll talk about what we, with Zing at Azure, can do to solve those problems. If we look at the JVM, what we're actually dealing with here is a managed runtime environment. This is the whole idea of shifting away from the way that things used to be done traditionally with programming languages. Going back to the beginning of Java 22 plus years ago, most languages were compiled directly into native instructions. So if you wrote in C or C++, you would compile your code into native instructions and they would run on the platform that they were compiled for. That meant that you had a lot of control over how things worked, you had the ability to compile based on certain options and so on, and you had a set of native instructions that would run. But it also introduced various problems which Java was intended to solve. Java took a different approach in terms of saying, well, let's do things differently. One of the things it does differently is it has a garbage collector. Memory management in C and C++ is dealt with by the programmer. So in C, you have to malloc. In C, you have to free up the memory that you've been allocated through malloc. In C++, you have to instantiate new objects, and then you as a developer have to remember to delete them when you finish with them. Java has this garbage collector. The idea is that a space is allocated automatically for objects when you instantiate them, but then you as a developer don't have to remember to deallocate that memory. The garbage collector will keep track of everything for you. It will then occasionally run to reclaim space that's needed to store new objects. The big thing about this is that it is inherently non-deterministic. What that means is that we can't predict when the garbage collector is going to run. Not only can we not predict when the garbage collector is going to run, we can't predict how long the garbage collector will take to do its work. So this makes life a little bit difficult from the point of view of trying to plan how your system is going to work, and also being able to guarantee the pause times that are going to be associated with the JVM and how that impacts on your application. What you can actually find is that pause times that you have due to garbage collection can be very big. The reality is that in most JVMs, as we'll talk about in a moment, that the pause times you get for garbage collection are proportional to the size of the heap, not the amount of data that's live in the heap. And that goes back to what I was saying in the last slide about why some Cassandra users actually tune for a smaller heap so that they can minimize the pause times. The second thing which Java does, which is different to traditional code, is that the compilation process generates these things called bytecodes. It doesn't compile into machine code, which is specific to a particular processor architecture that's specific to a particular operating system. Bytecodes are for a virtual machine, one that doesn't exist, but can be mapped to real machines at runtime. What this has led to is differences in terms of the way that performance works for using those bytecodes. So we have adaptive compilation, we have interpreting, and we're going to talk all about these things. But what this introduces is, again, differences in the way that we look at the speed of an application in terms of how the JVM affects that. So regardless of what our code actually does, the JVM will affect the performance based on whether it's interpreting the bytecodes, whether it has compiled those bytecodes, how it has compiled those bytecodes. And we get this classic idea of a warm-up time associated with an application. Now, I'd like to pause just briefly here to do a quick poll. So what I want to ask everybody who's online is, do you experience pauses with your Cassandra cluster? And the answers to that are yes, they cause us real problems. Yes, but we have tuned the VM to make them manageable. So you've done something with the VM in terms of the options you can use at startup. Yes, but they've not really been a problem to us. And then the last answer, which is no, I'm lucky. I'm one of these unusual people who have never seen a pause associated with Cassandra or a Cassandra cluster. So I'll just give people a few moments to answer that question. And then what I'll do now is hopefully everybody's had a chance to answer that. I'll just give you just a few more seconds. Wait, just a couple more seconds. And then, okay, if we close the poll now, then we can see the results. Oh, I can't see the results now. Hang on. So 50% said yes, they cause real problems, 25% yes, but have tuned the VM, 25% yes, but they're not really a problem. Okay, that actually kind of, yes, that kind of fits very nicely with what we experience with our customers. So the question is, what if there was a better JVM? What if we could solve those problems? And the answer is that there is, and that's Zing. Zing is the JVM which Azul have developed. What I'm going to spend the rest of this presentation talking about is what Zing does that's different to traditional JVMs and how that can impact on using Cassandra. And what we'll look at the end is real life effects by looking at some benchmarks that were done on actual customers and how it changed what they had in terms of their Cassandra cluster. So, first thing is to talk about garbage. Now, I mentioned the idea that we have this garbage collector, but the garbage collector is something which can be done in many different ways. And if you look at the Hotspot virtual machine that you have freely available from Oracle based on the OpenJDK source code, you will find that there are a number of different garbage collection strategies that can be employed. There's the parallel collector. This is designed for higher throughput, but potentially with longer pauses. There was the concurrent mark sweep collector, which is still there just, but is being deprecated in JDK 9. This was designed to give you lower pause times for more latency applications that had greater reliance on lower latency. That's been replaced more recently with the garbage first or G1 collector, and that uses a similar approach to the concurrent mark sweep, but does things in a different way in terms of the layout of the memory, which allows some concurrent compaction as well as the concurrent mark and sweep. And then there's some research. There's a project being run by Red Hat called Shenandoah. This is not yet in production, so nobody's actually using it in a real JVM, but that also has some interesting ideas about how to reduce latency and how to improve the performance of the garbage collector. The thing about garbage collection is that all the commercial garbage collectors, so all the ones that you can get in currently available virtual machines, will resort to what's called a full compacting collection if they can't keep up with the rate of allocation. G1 has made a lot of strides to improve performance, but it still has a situation where if it can't keep up with the rate of allocation and promotion from the young generation, it will actually have to stop application threads and it will do a full compacting collection. When you get a full compacting collection, that is when you see the really significant pauses, and the pauses at that point are proportional to the size of your heap, not to the amount of data in that heap. So how does Zing do things differently? Well, Zing is designed to solve the garbage collecting problem. What we don't do is follow any of the ways that people have used before. So we have no serial collector, there's no parallel collector, there's no CMS collector, there's no G1 collector. We have a collector that's called C4, the Continuous Concurrent Compacting Collector. And the most important thing about that is that the design of that does not have a situation where it says, I can't keep up with the rate of allocation, I will fall back to a full compacting collection. We simply don't do it. So you will not see these significant pauses associated with the size of the heap space. What the C4 way of doing things does is it uses a different approach, as I said. And what most collectors do is to use a write barrier. So whenever you want to change data in the objects that you're manipulating, there's an intercept to say, is this the right place that we want to make changes? What we do with C4 is we actually intercept every read that's associated with an object. So every time you try to use an object reference, we intercept that and we decide whether or not the reference is correct. That way, if we need to run garbage collection whilst your applications threads are running, we can do that. That means that we can move objects around, we can compact the heap space as the application threads are running. We don't see significant stop-the-world pauses, and we also find that with heaps, the bigger the heap, the better the results you get. So let's look at how that works in reality. So a little bit of technical detail on this, but it's useful to understand what I'm really saying here. So we have a set of garbage collection threads, and we have a set of application threads. And as I say, typically when the garbage collector runs on other VMs, what you'll see is pauses because the application threads can't run at the same time. When a garbage collection marking phase needs to be started, you will see a root set being created. And the root set is literally all of the directly accessible objects that you have from the objects that you're using in your stacks, in the direct references that you have. So the garbage collector will build this root set of directly accessible objects. Obviously, those objects are likely to have references to other objects. So you need to construct a graph of all the references from the root set to all the objects that are referenceable in order to determine exactly which objects are still being used and which objects can be reclaimed. So what the garbage collection threads will do is that they will start with that root set and they will mark a particular object as being used. So it has its bit set. Say this object is still being used, it won't be garbage collected. The references from that object will then be traced, and the objects that are followed from those references will be marked to indicate those as still being used. And then other garbage collection threads can also mark other objects and work on other objects. As the application threads are running, they need to be able to access objects. And as I say, we can do this concurrently. So if our application threads make a reference to an object, this may not be in the root set. This may be a new object that we've created, some object that we have, but we need to make sure that that is marked as being part of our still valid data. Rather than having the garbage collector do that, what we do in Zing is we say, have the application thread, when it uses an object and it hasn't already been marked, have the application thread mark that object. In addition, because that object may then have its own set of references that need to be followed, rather than having the application thread do that work, what we then say is pass that object on to the garbage collector so it can then trace all of the references and create this graph of objects. So we in effect get the application thread to do some of the work for us. Some people get a little bit concerned when we talk about a read barrier and the idea of this interception of every single read, because they think that might impact on performance. And yes, strictly speaking, there is an impact, but it's so small that it actually doesn't matter. What we do is, because we're only dealing with a single bit in the object reference, we can do a compare and jump. If the object has already been referenced, we don't need to do any work. So the overhead of that is literally a couple of machine instructions, so a couple of nanoseconds for every object reference. So you won't see any degradation in performance. If we have to mark it, there is a jump to the marking code, which will then mark the object. But that only needs to be called the first time the object is referenced from the application thread. So the overhead of doing this is very, very small. You really won't notice it unless you're doing some very specific things. What we then need to be able to do is relocate our objects. So we have blocks of memory, we have pages of memory, and there will be various objects distributed around there that need to be relocated. What we can do there is we can say, take our objects and compact them. So we calculate where we need to move the objects to in order to do the relocation. And then we can have our garbage collection actually run through and start moving objects. What we will do is, as we move those objects, we'll create a side table which shows where the object was and where the object has been moved to. That way, when we need to do the remapping phase, and this is where we need to go through and change the references of the object headers so that the object header points at the new position where we've compacted the object to rather than the old position, again, we will have our garbage collection threads doing some work in the background. What will happen is that the garbage collection thread will look at this side table and it will say object A was moved to A prime. So it will take the information about that and it will change the reference in the object header. It will do it atomically, so there's no problem with changing things and getting inconsistent data. And it will mark that object as having been relocated. So the object is now completely correct in that the header points to the right position. It can then go through and mark other objects. So it will go through and work through this table. If our application threads, which are running concurrently with the garbage collection threads, need to reference an object, we intercept the read. And so at that point, what will happen is we will try to use the object header. The object header will not have been marked as being remapped. So at that point, we do a compare and jump. We jump into the code that needs to handle the remapping. So the application thread will then allow that object to be remapped from its header. So it'll look up the position that it needs to be remapped to in the table. It'll copy that information and mark that object as now having been remapped. That way, it can then use the object reference in the application threads, having done that remapping, and everything is consistent. So we're able to move these objects around without having to pause the application threads. We can do it all concurrently with application and garbage collection at the same time. That way, we can eliminate these long pauses associated with compacting the old generation. The other thing about this is that it scales. So we can take any size heap up to 2 terabytes currently. We're working on going beyond that. But we can take a 2 terabyte heap and we can run compaction on that concurrently without having significant pauses. We don't have long pauses associated with that. So this is great because if you are running a cluster of Cassandra nodes and it would make more sense to make those nodes bigger and have less nodes, then you can do this. You can do it using Zing without having to impact on garbage collection pauses and therefore degrade the performance of your application. The important thing about this is often when I talk to people, I say, well, we can support up to 2 terabyte heaps. And people get the impression from that you need a big heap to run with Zing. And the answer is no, you don't need a big heap. It works well with them. And as I've said, you can actually get better performance as you increase the size of the heap, but you don't need a big heap. Literally, you can go from 1 gigabyte up to 2 terabytes. And the same algorithm will work and you'll get this pauseless garbage collection. So the second thing that we need to look at is how do we address the needs of bytecodes? So we talked about how garbage collection can interfere with our code. How does the idea of using bytecodes and interpreting and running just-in-time compilation affect things? So what adaptive compilation is about is taking these bytecodes, and initially the bytecodes will be interpreted by the virtual machine. Each bytecode will be taken and it will be translated into one or more instructions for the operating system. There's a direct conversion to machine code. This means that the code can work on any platform, but it doesn't work well in terms of performance. If you compile code in the old traditional way of doing things, compilers will perform optimizations based on looking at sequences of instructions. But with adaptive, with interpreting the bytecodes, these optimizations are not possible. So it's literally a one-to-one mapping, taking bytecode and then converting it into machine instruction. But that happens every time as well. So there's no caching of the results of conversion. There's no ability to improve performance directly that way. What now happens, and this is the idea behind the whole Hotspot virtual machine, is that the JVM, as you're running your application, will profile what bytecodes are being run, and more specifically, will profile what methods are being called and what classes are being used. If it sees a situation where you have a method that's being called repeatedly, so you have a loop where you're calling a method repeatedly, the profiling information will identify that as a hotspot. And the hotspot will then be passed to a just-in-time compiler. So the virtual machine contains what is in essence the back end of a compiler that can take the bytecodes and then compile those using the method rather than individual bytecodes. It'll take all the methods for a bytecode and compile those into native instructions. Those can then be cached so that the next time the method is called, no analysis has to be done. It's just reuse of the native instructions. Now, the way this works is that there are two different JIT compilers. There's what's called C1 and C2. The idea behind having two is that they have different profiles for the way they work. C1 is designed to have fast compilation so that you can get to the optimum level of speed as quickly as possible. However, because it does that, the optimum level that it gets to is maybe not as high. So it tries to do things as quickly as possible, but maybe not as efficiently as possible. C2 has a longer profiling and compilation process involved. So it takes longer to get to the compiled code, but the compiled code that's generated is more optimal. It takes the time to be able to analyze things in more detail, apply more optimizations, and get to a high level of performance. So in the past, what we've seen is you select either the C1 compiler or the C2 compiler, depending on whether you're doing a client application or a server application. In more recent versions of the JVM, that's been changed. So there's now what's called tiered compilation, where you start with C1, get to that optimum level of performance quickly, and then run C2 to increase the level of performance over time so you get better performance longer term. If we look at the impact that has on an application, this is a very typical kind of performance profile. What we're looking at here is the speed of your application. So lower graph means worse performance. And so if we look at that in detail, what we see is there's a yellow section at the front there, and that's where we're interpreting and profiling the code. So when you start your application, it starts interpreting the bytecodes, converts them as it needs them, runs them, profiles the code to identify some hotspots. What we'll then see is the green section where we've got the C1 JIT compiler working, it's starting to compile methods quickly, but the level of performance is not as high as we get with better optimizations available in C2. We then get into the phase where we've profiled a lot of code and we start to see the C2 JIT compiler working, compiling these frequently used methods, using the better optimizations and giving us a better level of speed. But we also see there are a number of dips in that graph. And there's two reasons for the dips in that graph. One is that as the compiler works, you get what are called de-optimizations. This is where the compiler is assuming certain things about your code as it compiles it. So it makes certain assumptions about how your code works, and it compiles to optimize for those assumptions. But sometimes those assumptions are going to be wrong, and your code will go down a different path, something will change, and the compiler then has to back out of what it's decided to do and revert back to doing interpreting before it can then recompile again based on the new way that your application code is actually running. The other set of things that we see drops in the performance of our graph are even when it has reached a steady state. And these are the ones which are related to garbage collection pauses. So even though we've compiled our code and we have a nice steady state, we're still going to see these drops in performance related to garbage collection. So what we have done is to look at how we can improve that. We improved garbage collection. How can we then improve the idea of JIT compilation? And fairly recently, we've released our Falcon JIT compiler. The reason we called it Falcon was because Falcon is the fastest animal on the planet. They've actually been measured at traveling at over 200 miles an hour in a dive. So we thought that makes sense. You know, we're aiming for the fastest JIT compiler on the planet. We'll call it Falcon. What we did for that was we didn't start from scratch. We looked around and we found that there's an open source project called LLVM. This is a compiler project that is being used by many different companies. There's people like Apple, there's people like Microsoft, Intel, NVIDIA, ARM. Many companies are involved in helping to develop aspects of compilation. And this is really good because it's open source, so we can use it in our code. But it's also taking advantage of all the input from engineers from these companies like Intel, like ARM, where they understand exactly how the processes work. People like Red Hat, people like Microsoft who understand how the operating systems work. So a lot of know-how goes into the development of this. What we've done is take that and integrate it into the JVM. Now, that took some work because clearly the code was originally designed for a more traditional kind of compiler. So we've integrated it with a JVM where it needs to work in a managed environment, and then we push those changes back into the open source project. So we're being good open source citizens in that respect. What this gives is better performance. So we can do better use of intrinsics around how the code is generated. We can do more inlining of the code. So we can take methods, we can inline them, and we can have fewer excludes from the way the compiler works. So this is essentially a replacement for the C2 compiler. Now, if we look at a little bit more detail, let's look at an example here of how this might work. This is a very simple method that takes an array of integers and adds them all up. So it creates a sum of the values in that array. This is the kind of code which a normal traditional JIT compiler can optimize very efficiently, because it can look at that and it can say, I can use modern processor instructions, specifically what's called vectorization, where you have a single instruction, multiple data. It uses very wide registers of 128, 256, even 512 bits, loads that up with several integers at the same time, and can then use a single instruction on multiple elements of our array to allow us to add up several things in one instruction. So as I say, traditional compiler processes this without any problem. If we make that loop a little bit more complicated, what we're going to do is we're going to have two arrays now, and we're going to say, let's check the arrays are the same length. But then we'll iterate through that first array, we'll iterate through the second array, and we'll say, if this is an even number, add it to the equivalent element in the first array. So it's just a slightly different way of doing things, a little bit more complicated. Now, because of the way this works, for your traditional JIT compiler, it won't be able to look at that and go, oh, I could apply optimizations of the most extreme type to this. So it'll have to use less beneficial optimizations. So we look at, again, a little example of code here. I'm not going to go into huge detail here, but this is the kind of machine instructions that are generated by a typical JVM JIT. So there's a block of code here which relates to part of the code that's being executed for this method. And if you drill into a little bit more detail, what you actually find, without going into the real nitty-gritty here, is that there are actually two elements being processed each time. So this is doing what's called a loop unrolling, which is another very common way of optimizing compilers. So it unrolls a loop and says do 2 iterations every time to halve the number of iterations that has to be done and improve the efficiency that way. So that's all the optimizations it's able to do, is to do 2 elements per iteration of our loop. If we take the same code and we apply Falcon to this, now we're going to run this on a Broadwell processor. What we can see here is it actually looks like there's more instructions. This block of code is slightly bigger, so you think to yourself, well, there's more instructions here, so isn't that not as good? But what you'll actually find is that the code there is broken down into a number of instructions for handling an iteration of an element on the array. That consists of 6 instructions. And what we can see here is we've got 6 instructions, but they're repeated 4 times. So now what we're doing is we're actually doing 4 iterations or 4 elements of the array for each iteration compared to 2 that we were doing before. But it's actually more than that because we're using vectorization, we're using the AVX2 instruction set, which gives us 256 bits in our register. By loading integers into that register and then doing 4 processes on each iteration, we're actually able to process 32 elements of our array for each iteration of the loop. And that's compared with 2 that we were able to do if we didn't have this optimization available to us. So this is the kind of thing that Falcon can do. It can take advantage of newer hardware. It can take advantage of improved ways of optimizing our code to get better performance out of things. And one of the real key things about Falcon is the design using LLVM is modular, which means that it's much easier to add new features. And as new features become available through the work that's being done in the LLVM project, we can include those very easily into the Zing JVM. The last thing I want to talk about is what's called Ready Now and how we can avoid application warm-up. So this, again, is the graph that we saw earlier. So we look at speed and we know that we have interpreting at the beginning. We then use C1 JIT to compile some code, do some profiling. We switch to C2, we do more profiling, we do more compilation, we hit these de-optimizations. And this means that we have a warm-up time associated with our application. If we start our application, we're not going to get the optimum level of performance until it could be several minutes after the application has started running. And if you're running in a situation where performance is critical and you don't want to have sluggish response times as the system starts up, this can be a problem. People often take the approach of going, okay, well, we want this system to be ready at, let's say, 9 o'clock in the morning. Let's start it at 10 to 9. We'll run it with some sample data. We'll preload things and we'll get it to warm up before it's actually needed at 9 o'clock in the morning. That kind of works sometimes, but the problem is that if you're using simulated data, you might not get the real effect of what real data is. And so there are all sorts of issues with doing that. So what we have is a thing called Ready Now. And what Ready Now does is it says, okay, you run your application in a real environment. So you run your application, you let it go through the warm-up phase, gets to a nice steady state, runs with your data, it's running real data, real workloads, and the JIT compiler and the JVM have a very clear picture of exactly what's happening. What Ready Now will do is it will save the profiling information associated with your application. And there are really kind of 4 things which get saved there. One is which classes are loaded. Second thing is which of those classes are initialized. There's some instruction profiling data, which is things like which methods have thrown a null pointer exception, various things where you've got exceptions or things like that. And then there's information about which speculative optimizations didn't work. So things that had been tried by the compiler but had to be backed out. By saving this information, we can then use it again when the application restarts. People often think that wouldn't it be a good idea if we simply took the compiled code that the application has as it's running, save that as a snapshot, and then reuse it when the application starts up. And the reality is you can't do that. The way that the JVM specification works is it says that you can do lazy loading of classes, so you can say, okay, well, we'll load the classes as before they're needed, but in terms of initialization of classes, they have to be driven by the creation of an instance of that type, or it has to be a static reference to a method or a static reference to a variable. You can't pre-initialize classes the way that you would need to in order to use saved code. Also, you would get issues with the way that the saved code works. It's not as optimal. So what we do is we save the profiling information that is used by the JVM internally. When you restart your application, we then have a picture which is based on a long run of your application. JVM, the JIT, the profiling information that's generated to be used by the compiler tends to be gathered over a shorter space of time, because it's the idea you want to be able to compile that code as quickly as possible. Even the C2 compiler, which will take longer, still uses a relatively short profiling period to gather data before it starts compiling. By using information that's been gathered over a longer running of the application, we can get information which allows us to reduce a lot of the de-optimizations that would occur naturally, because you've got this steady state of data, you've got the data that you're using for your application in a real world situation, and we can avoid literally 80% of the de-optimizations that you would see happening if you compile your code using the JIT and allowing it to warm up. The other thing about this is we're actually able to take this information, and then because of the way that we can use this, we can actually load, initialize, and compile most of the code that's necessary, not all of it, but most of it, before the main method is called. So this allows us to say, well, okay, so you start your application a few minutes before it's needed, you'll get to the main entry point, and you know at that point, pretty much all of the classes are loaded, all the classes are initialized, and the code's been compiled. So you really reduce the warm-up period associated with once you've got to the main entry point. Yeah, it takes a little bit longer to actually do the warm-up before you get to the main point, but we have tools that tell you when the code is ready, and so you will be able to then run your application at full speed. This is the sort of graph that we see typically of before and after using Ready Now. So the orange line shows how the compilation is working. So we're doing some optimizations, then we're de-optimizing until we get to a steady state. Even when we're running, we're seeing a number of de-optimizations that kind of kick in there. The blue line shows after we use Ready Now. So we're able to take advantage of the long knowledge we have of how the application runs and really flatten out the latency that we see with the application. So let's talk a little bit about Cassandra running on Zing and look at some kind of real world examples of how this actually changes. So the first thing is, let's look at the typical tuning that has to be done with Hotspot. And it's interesting because in the poll earlier, I said, had people had to use a number of tuning options to eliminate or alleviate the pauses that they get with the VM. And so typically you set maximum heap size, so 16 gigabytes in this case. And this is a set of options that were taken from a real world deployment of Cassandra. So 16 gigabyte maximum heap size, but then they needed a few other options around that. So you get things like this. It's using parallel new garbage collection, it's using concurrent mark sweep, it's got concurrent mark sweep parallel remark enabled, survivor ratio of 8, lots and lots of options. And trying to figure out all these options can be very difficult. It can be very difficult to know, well, should my survivor ratio be 8 or should it be 128? Unless you do it by trial and error, it's very difficult to know exactly how to make this work. Let's look at the same thing if we tune Zing. So we'll start with the same option, which was going to set the maximum heap size to 16 gigabytes. Then we'll need all of the other options that make Zing work properly, and we'll see what those are. No, 1. We'll just tell it to use large pages. So that'll optimize the size of the page that's used for Zing. So this gives you an idea of how well Zing works. We don't need all of these extra options to tell the garbage collector all these different little knobs that need to be tuned. We simply say, this is how big the heap needs to be. In this case, we're going to use large pages to optimize the underlying OS way of doing things, and that's it. You just let the Zing C4 way of doing things work, and it will optimize for you. The other thing is, how do we measure performance? And the problem here is that if you try measuring performance of an application, you can use benchmarking tools and you can look at how your application works. But what that's going to show you is the impact of the whole system. So it'll be your application, it'll be the JVM, it'll be the operating system, it'll be the hardware. Several different layers involved. If we're interested to see just how the JVM performs and how that impacts your application, we need a different way of monitoring things. And this is why Azul came up with a thing called JHiccup. JHiccup is a very simple tool which allows you to see the effect of the JVM, the operating system, and the hardware on your application. So not what your application is doing, but what everything underneath your application is doing. The way it works is that it's installed as a class which runs in the same virtual machine as your application, but it runs in a separate thread. So it doesn't interact with your code at all. It's simply running alongside it in the same JVM. It spends most of its time asleep. So the idea is to minimize the impact of performance so we don't have Heisenberg's uncertainty principle affecting us. What it will do is it will wake up every 1 millisecond, and it will know what time it went to sleep, and it will look at what was the difference between when it expected to wake up and when it actually woke up, and it will record that difference. Because if it expects to wake up exactly 1 millisecond later and a garbage collection pause kicks in, application threads aren't able to run, so the application thread will be delayed until the garbage collection has completed, at which point the JHiccup thread will wake up, it will see the time is further down, and it will then record the difference. What this allows us to do is to see exactly what effect the JVM has on your application. And then we can take this information, we can generate histograms of that, we can log files, and then we can graph that to see the effect over time of the JVM on your application. So here's an example. This is Cassandra being used by a large payment company. I'm not in a position to give names, but it's a large payment company. And we have Hotspot running with 24 client threads. We have Zing running with 24 client threads. And as you can see, what we see on the left is we see Hotspot has, quite a significant peak there, and then there's a lot of smaller peaks about in the middle, which is latency. So this is high means bad, because that means that you're having to delay your application by a certain amount of time before it can produce a response. And then on the right, we've got Zing, where we've got one big peak there, and then we've got a few smaller peaks down at the bottom. I deliberately showed this graph first, because if you look at the two side by side, you say, well, okay, they kind of look, okay, the Hotspot one definitely looks worse, but, there's still that big peak in the Zing graph. So how is that much better? But what you also need to look at is the scale of the graph. So if you look at the scale of the left-hand graph, that has a peak which is 100 milliseconds. So the highest peak we see there is 100 milliseconds, and we're seeing most peaks in the 40 to 70 millisecond range. The Zing graph has a different scale. So we actually have a peak of 8 milliseconds. So that's right near where the green line is on the Hotspot graph. And that's one peak of 8 milliseconds. Most of our peaks are less than 1 millisecond. We've got a few that go just over 1 millisecond. So that's the difference we're dealing with here. Most of the graph being around the 1 millisecond pause time for Zing, most of the graph being in the 50 to 70 millisecond range for Hotspot. That gives you an idea of the difference that Zing can make. So again, if we look at some other results, this is a large retailer that we work with, and they were using G1, so the most modern garbage collector in Hotspot, running their system. So they're a 64 gigabyte heap. They tried it with Zing using C4, again, 64 gigabyte heap. And what they saw with their system was new gen, so the young generation garbage collection pauses, 200 milliseconds every 2 seconds. That means it's spending 10% of its time doing garbage collection. And then the old garbage collection, old generation garbage collection, every 6 hours they were seeing a 1.8 second pause. If you're trying to deliver results quickly, 1.8 seconds might not seem like a lot, but it can be a very significant thing in certain situations. With Zing, they were able to scale the heap size much bigger without any degradation. All the pauses they got were within 7 milliseconds. So that's way, way lower. And again, if we look at some graphs of this, what we're seeing here is in a particular Cassandra node, left-hand side, we've got Hotspot. Back there. Left-hand side, we've got Hotspot, and what we're seeing is that most of the graph is in that sort of 200 millisecond range. So this is it spending 10% of its time doing garbage collection with a one spike up there of like sort of a second and a half almost. On the right-hand side, we've got Zing. Now I've scaled the graphs to the same scale, and you've literally got a flat line at the bottom. You can't see where the graph is on Zing because it's around 7 milliseconds. So it doesn't even register on a graph compared to what you're seeing on the left with Hotspot. Looking at a slightly kind of more involved example of what we were doing there, this is using Cassandra, Solr, running on Docker. Again, what we're seeing here is a couple of graphs of Hotspot running. We're seeing some really significant pauses. That's 17.5 seconds as a peak there. A lot of pauses in the sort of 7 to 10 second range, and many in the 5 second range. Most of it is in the 5 second range, or a couple of seconds below that. But really long pauses for something which needs to be available all the time. You know, the other graph, okay, we've got slightly lower values there. We've got a peak of 10 seconds. We've got a lot of peaks around the 5 second range. But again, we look at the Zing equivalent graph, and suddenly it's just flatlined. It's dropped down to 0, and we're not seeing any problem with that. So this, again, is the key thing of what we can do with Zing to eliminate the problems of latency and performance issues of the JVM around Cassandra. So just to conclude, if we go back to our graph that we saw earlier, what we do with Zing is change the shape of that graph. So we saw that we had, initially we start off in interpreted mode, then we use C1, then we use C2. And we see some pauses or some drops in performance due to garbage collection. So in terms of what we can do is we can shift the problem. So we eliminate a lot of the pause or a lot of the drop in performance of the warm-up period by using Ready Now. So we can load classes, we can initialize classes, we can compile methods very, very quickly. So that shifts the shape of the graph, pushes it right up so that we get performance very quickly once we start the application. Falcon allows us to push the envelope even further up. So we can do optimizations beyond what we could do with the traditional C2 compiler and actually raise the level of the speed that we get by using Falcon. And then C4, as I said, eliminates these drops in performance due to garbage collection. So we have a much nicer looking graph using Zing than we would with a traditional JVM. We can eliminate almost all the problems that you get in terms of performance of the JVM itself affecting your application. Zing JVM, the idea here is like starts fast, goes faster, stays fast. This is ideally suited to Cassandra performance issues. And if you go to our website, you can actually get a free trial of our Zing JVM. You can sign up, you can get 30 days free trial on there, and you can install it, you can test it, see what happens with your application. We have a, as I say, free trial that you can use there. So with that, let's see whether we have some questions, because that is pretty much the end of the webinar. So we have questions. Right. Not a question. You should have an option, not a problem, as I use Zing. Oh, I see. Right. Yes. People who are already using Zing. Another question regarding the sorting of records in Cassandra, how it works. Okay, that's a bit difficult to answer because from the point of view of how Cassandra works on top of Zing, there is no difference. So the way that Cassandra is actually operating is exactly the same as it would be running on top of Hotspot. So there's no difference in terms of the way that sorting would work or anything like that. I think that's the only answer I can really give to that question. Let's see, another question here. Can Falcon use AVX 512? Yes, so this is the most modern processor. So if you look at like the Skylake processors from Intel, they now have the idea of the AVX 512 instructions, which are have a register which is 512 bits wide, which means you can load a large number of integers at the same time. And then, as I say, single instruction, multiple data, you can process those things and have those work. So I don't see any other questions. So I think since we've covered everything, that we will wrap up the webinar here. So thank you very much for attending, and thank you. Bye-bye.